Okay, so this time we're going to consider the case E is less than V0. We'll send a plane wave in as before from the left. And by the way, when I'm drawing the wave functions here on this plot, it's really a bit of a mix of two different diagrams. In the picture here, this is showing the potential. So the y-axis here is the potential as a function of position. I'm drawing the waves coming in like this. And of course, really, I'm plotting the amplitude of the wave function in the region as a function of position. It's a very mixed notation, but it's something that we tend to do. Hopefully, the idea is clear that this is a wave coming in, and this just happens to be the potential landscape it's moving in. Now, this is phi in, coming in this way. As before, we'll get a phi reflected coming back. But this time, because E is less than V0, the region over here is what's called classically forbidden. So if we just take a step back for a second and think about what would happen classically, the potential here could be something like a height. A height is a gravitational potential. So we could have a height that's 0 over here and then V0 over here. And so this would be like some kind of wall. And if we send in a classical particle, as in, say, throw a tennis ball in the direction of a wall, if the tennis ball has this energy, a gravitational energy that's larger than that of the wall, as in it's going over the wall, then sure, it can go over here. But if we send in a tennis ball whose gravitational potential energy is less than that of the top of the wall, it should bounce back. Of course, this is then classically forbidden. Tennis ball can't go into the wall. In fact, we'll see that in the Schrödinger equation it's allowed. The form of the solutions are evanescent type solutions, exponentially growing or decreasing. And in this case, only the decreasing solution can be relevant. Again, not worrying too much about the fact that I'm mixing my notations with potential and the wave function. So we're going to have an exponentially decreasing amplitude over here. Or rather, an exponentially decreasing wave function, because otherwise the wave function would have to blow up at infinity if we allow the positive solution. This barrier just goes off to infinity. Okay, so let's take a look at solving this explicitly and looking at the classically forbidden region. Okay, so we'll go a little bit faster than we did in the last one, but the working is very much the same. So in region 1, we'll have phi 1, which is equal to phi in plus phi reflected. And this can be written as e to the I kx plus re to the minus I kx, just as before. Nothing's changing in region 1. Substitute it into the time-independent Schrödinger equation, and we'll find that E equals h bar squared k squared over 2m, just like before. In region 2, however, we'll have phi in region 2 is equal to phi transmitted. Remember, t for transmitted, not for time or anything like that. And this is equal to t e to the minus kappa x. Kappa used instead of k, just to indicate that it's really a different quantity to a wave vector. Substitute it into the time-independent Schrödinger equation in region 2, and we find that E equals minus h bar squared kappa squared over 2m plus v naught. So the minus here coming from the fact that there was a minus already in the time-independent Schrödinger equation, and we don't cancel it with an I squared as we do in the case of plane waves. Okay, so boundary conditions as before. The first boundary condition is that the wave function is continuous. So phi in region 1 at x equals 0 is equal to phi in region 2 at x equals 0, which tells us that 1 plus r equals t, just like before. Boundary condition 2, the first derivative of the wave function must also match. The first derivative is also continuous. And in this case, what we find this gives us is that I, k, 1 minus r, that's what we got before in region 1, is now equal to minus kappa t in region 2. So a slightly different form. In fact, rewriting, we have 1 minus r equals, multiply through by minus I, we get I kappa over k t. Just as before, we have two equations, two unknowns, r and t, the amplitudes for reflection and transmission. Remember, kappa and k are both already known from kappa from this equation, k from this equation. And we can, using these two equations, we can derive the probability for reflection, which is k minus I kappa over k plus I kappa, and the probability of transmission is 2k over k plus I kappa. In fact, if you compare to the results we got for the case that energy was greater than V0, you'll see that because all we've really done is we've changed what was e to the I k prime x to e to the minus kappa x, we've just changed I k prime to minus kappa, and if you make those substitutions you'll find you get the same results. Alright, so let's flip the page around and look at the probabilities. So those were the amplitudes. Actually, let's just comment on this quickly. So we have the amplitude for the particle to exist in region 2 is non-zero. So remember, region 2 is classically forbidden, but there's nevertheless an amplitude to find the particle there. What that means is that if we perform a measurement, we could find the particle in region 2. How does this tally with the fact that there isn't enough energy for the particle to be there? The answer is that our measurement device will provide the energy if it's to observe the particle. And really what we're doing is changing the boundary conditions on the problem. We're changing the potential when we make the measurement. We'll see more of that in the quantum tunneling problem in the next video. Nevertheless, let's take a look at the probability for the probability current densities in the different regions. So let me just write this down like this. There we go. Partial subscript x again means d phi star in this case by dx, holding time constant. And so what we get is that phi for phi in, which equals e to the I k x, substituted into here, and just as before we find j in equals h bar k over m. Phi transmitted equals the transmission amplitude e to the minus kappa x. Substitute that into here. Let me just write it out like this again. So we substituted phi and phi star into here. Evaluating it, we find this. So we bring down a minus kappa in both cases, but now the minus sign between the two terms, remember it's this term minus the complex conjugate, but the two terms are the same because phi is now real. And so actually we find that these perfectly cancel out, and we find that j transmitted equals 0. And so therefore the probability of transmission, which is equal to jt over j in modulus, is equal to 0. This is what we call the probability flux. The probability that the probability current density is going to create a travelling wave in the classically forbidden region. So even though there's an amplitude to find the particle over there, the probability current density is 0. So there's no current propagating through that region. If we look at the probability for reflection, which is j reflected over j incident, in fact, the expression is the same as we found in the last video, still modulus r squared. And if we substitute it in, we find for r we had k minus I kappa over k plus I kappa. And if you do the modulus square of this, you'll find out that it equals 1, which must have been the case because the probability of transmission plus the probability of reflection is always equal to 1. From conservation of probability. Okay, thank you for your time.